Hello, this is Nick Ballou, and I am doing a MIDAC demonstration for the Thevenin and Norton Equivalent Circuits Lab. First, to give a little bit of background about the subject matter, the Thevenin and Norton equivalent circuits are useful for simplifying a circuit. For instance, this circuit here has several resistors in series and parallel, and if you were just analyzing the load resistor here, it could be complicated considering all the resistors. So what a Thevenin and Norton equivalent circuit does is it simplifies the circuit. So this is a Thevenin equivalent circuit where you reduce all of the resistors that are in series and parallel into one voltage source and then a resistor in series with the voltage source. And then this is a Norton equivalent circuit where you reduce all the resistors and the voltage to a current source in parallel with the resistor. And how you accomplish figuring out the Thevenin and Norton parameters is first you disconnect the load resistor, and then you determine the open circuit voltage across those nodes, and then you put a wire across the load resistor and you find the short circuit current. And then you use these equations right here. So the Thevenin resistance is the open circuit voltage divided by the short circuit current, and that's also the Norton resistance. And then the Thevenin voltage is equal to the open circuit voltage, and the Norton current is equal to the short circuit current. So the first part of the lab is a computer simulation pre-lab portion, and you simulate this circuit shown right here using multisim or some other software. So here is the circuit using multisim, and you can put in the meters to measure the current across all of the elements, and you can measure the power across all of the elements. Also, now to calculate the Thevenin and Norton parameters, what you do is this is the load resistor right here, and you can remove that, and then you find the open circuit voltage across those nodes, and then after you find open circuit voltage, you put a wire across those nodes, and then you find the current, the short circuit current, and then you can go back and use those equations that we talked about earlier, and then you can find the Thevenin and Norton parameters for the circuit, which greatly simplifies the circuit. So that is the pre-lab portion. Oh, and also for the pre-lab, you can also, once you find the currents across all of the elements, you can also verify that the power dissipated by all of the elements equals the power input into the system by the voltage source. So next we move to the actual lab portion, and you can demonstrate the Thevenin and Norton equivalent circuits using the MIDAC system. So here is, so this is the base circuit that we're using. That's a schematic example of it, and then here it is on the MIDAC. As you can see, we basically have a lot of wires in the way. So in here we're using the 5 voltage as the source, and then basically we have 3 resistors in series, and then you have 2 resistors in parallel. So we have a total of 5 resistors, and this is the load resistor. So the first part of the lab is measuring the resistance of each of the resistors. And how you can accomplish that is if you pull up the NI Elvis toolbar or instrument launcher, you can pull up the digital multimeter, and there is an ohm meter as part of that. And what you can do is you can put in the resistor separately, and this is hard to do one-handed, but you can I might not be able to do this, but you can put the probes across the resistor, and then the value will show up on the can't do it one-handed, but if I had 2 hands, the resistance would show up there on the meter screen. So once you find the resistance of each of the elements, then you also measure the voltage and the current. So if you go back over to your multimeter, there's you can see there's a button for a DC current, and there's a button for the DC voltage. So if we go to the current, what you can do is across each of the elements, again I can't do this one-handed, but you put the probes across the 2 ends of each of the elements, and then that'll give you the current and the voltage when you switch out the multimeter settings. And what you'll get is a series of values. You'll see here you have resistance values for each of the resistors, and then the voltage and the current. And then the next part of the lab is finding the open circuit voltage. As shown in here, you remove the load resistor. So what you do is you remove that guy right there, and then you can put in the probes and measure across the nodes where that resistor, the load resistor, was. And then if you do that, and this, in the case with the resistors I'm using now, you get 2.38 volts. And then the next step is you can replace the load resistor with a wire, and then you measure, using the probes again, the current across that wire. And in this case I got 0.62 milliamps. And then if you want to find the thevenin resistance, you divide those 2 numbers and you get 3.8 kiloohms, which is close to the requested 3.9 kiloohms given in the instructions. And then the next part is you can actually measure the thevenin resistance directly on the circuit board. What you do is you remove the voltage source, and then you measure the resistance across the nodes. So what you can do on the circuit board here is you can remove the voltage source, and then again, this is one of those things that's hard to do one-handed, but you can put in a wire across and short the voltage source. So then you can just go back and remove the load resistor, put the probes across those 2 nodes, and measure the thevenin resistance. And in this case, it came out to be 3.87 kiloohms, which is close to what was calculated before at 3.8 kiloohms. The next part of the lab is to find the maximum power, the resistor that gives you the maximum power output. And what you can do is you take the load resistor out and then you can replace it with multiple other resistors. I had between 1 kiloohm and 10 kiloohm resistors, and you can measure the current and the voltage across the different resistors. And what you should end up with is that the maximum power occurs at the resistor that has at the thevenin resistor voltage. So in this case, the thevenin resistance was around 3.8 to 3.9 kiloohms, and then when you plot the data, the curve comes up around 4 or so. So the experimental values agree with the theoretical values. Finally, a challenge part of this lab is to use a potentiometer that we have here, where you can use it to vary the resistance using one component instead of multi-components. So the challenge here is to redo the last part of the lab where we find the maximum power using the potentiometer. And what you can do is you can measure the resistance, you can change the resistance using the top switch, and then you can measure the resistance across the elements, and you can use this instead of the resistors, and you can find a more continuous curve. So that's the challenge part, is to redo this lab using the potentiometer. And that is it for the demonstration part of this laboratory. Thank you.